some basic type of optimization algorithm. So this is just an introductory thing. Later, we'll go into detail into this various type with examples. So first is called exhaustive search. Put reading. The exhaustive search algorithms will search the entire domain exhaustively with a fine increment, searching for the maxima or minima. So how this works is that, okay, suppose this is our objective function. Okay, so this is f of x versus x. So this x-axis is divided into very fine increments like this. Okay, so you have to start from the left and search each value of x, and you have to check this altitudes. Okay, from left to right, and because this x-axis values are have very fine intervals, you will definitely find all these peaks, but it is exhaustive search. So in actual practice, you cannot do exhaustive search for this entire range. You have to first narrow down some range, and then you have to do exhaustive search within that range. So that is the first type. Another is called grid search method, which is a type of exhaustive search for two or more variables. So that is both x and y variables are there. So what is happening is that this domain is divided into a grid like this. So x-axis is here and y-axis here, and it is divided with a fine increment like delta, fine increment delta. So the user has to start at a particular point like this, and the user has to sample the objective function at the four corners. So you have to check f of xy at the four corners. Okay, and suppose you get least value of f of xy here. So now you come here and again you search this four corners. Okay, and suppose the next least value of f of xy is here. So then you go here. Okay, so you go to the grid point which has the least objective function value, and you continue until you reach the smallest value of the objective function. Then another method is hill climbing method or calculus based method or analytical based method. So this depends on checking first and second derivatives. So what you do is that suppose this is your objective function, the user has to pick a starting point. Suppose starting point is here. He has to find the slopes on either side, like theta and whichever is the steepest slope, the algorithm will climb, and it will always check the first derivative. So when first derivative is 0, it means that you have reached the peak. Okay, then you have to check second derivative to see if it is maxima or minima. So this is called hill climbing methods or calculus based methods. So the disadvantage of calculus based method, which you'll study later, is that the user has to give starting point and it will only calculate the peaks near the starting point. And another is purely random search. So the entire domain is searched at several randomly selected points. So f of x value is searched at some randomly selected values of x. Okay, and you know you have to check if the objective function value is minima there. So the locations where maxima or minima is likely to occur is found out, and this can be given as a starting point to the grid search or analytical method. So that is the only use of the random search. With the random search, you can never hope to find the exact maxima or minima except by luck. So random search can be used to pick a promising starting point and give it as a starting point to this exhaustive search, grid search, or analytical methods. Okay, then heuristic algorithms, these are highly important. Nowadays, everybody uses this heuristic algorithms only. So simulated annealing. So all these heuristic algorithms will imitate some rules of the nature. So heuristic means rule of thumb or approximate method. So simulated annealing was an old optimization algorithm which emerged in the 1980s. It was first of the heuristic algorithms, and it simulates the slow cooling of heated metal. Next is genetic algorithm, which came like end of 1980s. So it is based on survival of the fittest. So you generated lot of random solutions. You take the best solutions from the top and you reject the worst solutions from the bottom. And these best solutions are subjected to some sort of interpolations and all to get the next best solutions and so on and so forth. Then particle sum also will study, if time permits, which is the social behavior of birds. So a flock of birds will see, when flock of birds fly through the air, they see different food targets. So one food target is the best one. That is called the globally best food target, and the other food sources are all locally best food sources. So this swarm of birds will, after some iterations, converge to the globally best food target. So that is imitated by this particle swarm algorithm. So how that is done, we'll see toward the end of the syllabus. So all these heuristic algorithms have use a combination of some form of random search with a sense of direction. So this heuristic algorithm is a mixture of a random search as well as some sort of logic. Okay, like in the genetic algorithm, which is called survival of the fittest. But you start with a random solution and then apply survival of fittest to that. So it incorporates randomness as well as some logic. So they don't get stuck in a local optimum. So that is the success of this algorithm. And attributes of a good optimization algorithm. So first is it should be robust and reliable. So now, what is the meaning of these terms? Okay, robustness means it should be numerically stable, and reliability means it must give the same results from run to run. Okay, suppose I want to find the maxima of a objective function with a calculus based method. I give one starting point and the algorithm gives one maxima. Then I again repeat it with another starting point. The algorithm gives another maxima. So that is not a reliable or robust method. But genetic algorithm and all will give same results again and again. Then efficiency means fast convergence in fewer iterations. Generality means it must be applicable to many problems. Okay, for example, it must be applicable to linear as well as non-linear objective functions. So if you use something like linear programming method, it can be used only for linear objective functions. If the objective function has non-linear terms, then this linear programming method will not work. So that is not a generalized method. And it must be easy to use. Then how do you formulate the optimization problem for engineering application? First is you have to identify the need for real optimization. So typically in the industry, when somebody says they made optimized parts, it simply means they did some trial and error with different type of parts and arrived at the best combination. So that is not really optimization. So optimization here means optimization using an algorithm. So you have to identify whether you need that. Then you have to choose the design variables carefully. Okay, like if you want to minimize the volume of a beam, it should be length, breadth, height, etc. Then choose constraints. That is, stress should not exceed such level, deflection should not exceed such level. Then you have to formulate the objective function like weight or like surface area, or minimize the stiffness or something like that. I mean, maximize stiffness or something like that. You have to formulate the objective function, and this design variables must be a part of the objective function. Okay. And establish the bounds of the variables, like length should be between 1 meter and 2 meter and things like that. Then choose an optimization algorithm which is appropriate for the problem. So if it is some linear, objective function is linear and constraints are linear, you can choose linear programming method. And if your objective function has lot of local and global peaks, then you should choose genetic algorithm. Otherwise, if you use calculus-based method, it will be stuck in the peak nearest to the starting point. Then you must be able to interpret the results. Okay, then choosing the design variables. So design variables are also called optimization variables. You have to choose the design variables which are sensitive to the problem. Okay, so usually choosing the design variable is not a difficult task for ordinary problem. For example, for beam weight, it is obvious that length, breadth, and height are parts of the are the design variables for the beam weight. But some complex engineering problems are there. For example, suppose you want to minimize the drying time for paint. Okay, drying time for paint. Okay, then so many design variables may be there, like atmospheric temperature, atmospheric humidity, then the density of the paint, viscosity of the paint, then the cleanliness of the surface. So you have to use some sort of sensitivity study and find out which variables are important for this objective function. Then more variables, more difficult it is for the algorithm to convert. Suppose your objective function has 10 variables, then the algorithm will struggle very much to find the suitable solution. It will struggle to converge with these 10 variables. Then choosing the objective function. So objective function must be function of the design variables. So all the design variables like length, breadth, height must be there in the objective function. Then the objective function is formulated with in terms of maximizing or minimizing the goal. Then we can use duality principles for certain optimization algorithms. Okay, maximizing problem can be converted to minimizing problem. So like I said earlier, some optimization algorithms will do only minimization. And if you want to do maximization problem, what you have to do is that you have to take negative of the objective function and give it to the algorithm. Then it will minimize the negative of the objective function and you'll get the maximization. Now that is a useful trick. Then we can have one objective function which is called single objective, or we can have multi-objective, that is more than one objective function. So multi-objective functions, as I told earlier, sometimes we may have two or more conflicting objectives like minimize weight and at the same time minimize deflection. Okay. So sometimes these objectives may have different units, like weight is in kilogram, deflection is in mm. So they have to be normalized by a weighting factor. So the expected weight should be divided by the average weight you expect in the feasible domain, and the expected deflection should be divided by the average deflection you expect in the feasible domain. Then we can make a combined objective function using weighting factors. Okay, suppose h1x is the objective function for weight minimization, s2x is the objective function for stiffness minimization. Okay, so you can write combined objective function w1 into h1 plus w2 into h2. But w1 and w2 are the two weighting factors. So sigma w should be equal to 1. So w1 can be 0.5, w2 can be 0.5, or w1 can be 0.6, or w2 can be 0.5, or w1 can be 0.9, w2 can be 0.1. So you can see each combination of it will give a different solution. So you have to try all these combinations and find which one gives the best results. So it is difficult to know which is the correct weighting factor in advance. So usually different combination of weights have to be tried. Then for conflicting objectives, the exact method is to find the Pareto front, which we'll study in the end of the syllabus. Suppose these are the two objective functions h1x and h2x. So they are conflicting objectives. Okay. So when h1 is minimized, this h2 will go up. And when this um, uh, h2 is minimized, this h1 will become a maximum. So this Pareto optimal front gives the range of best allowable minimum combinations of H1x and H2x. So all points on this Pareto optimal front are solutions to your problems. So any point here will give a good combination of H1 and H2. Okay. So to find this Pareto optimal front requires a lot of computational effort. So that will study in the end of the syllabus. Okay. So once you find Pareto optimal front, you have infinite number of combinations for H1 and H2. Okay, so this is one combination of H1 and H2. This is another combination of H1 and H2. This is another combination of H1 and H2, and this is another combination. Now, so all these combinations will satisfy your constraints, and you can choose any one of these combinations. Then constraints. So design limitations are expressed as constraint equations like space, that is the length, breadth, height should not exceed certain values, then stress should not exceed certain values, deflection should not exceed certain values. So that is called constraints. Then so remember the consequences of too many equality constraints. So in yesterday's lecture we saw that equality constraints will drastically reduce the feasible region. So you should give as little equality constraints as possible. Okay, then another type of constraints is the variable bound. Suppose x and y are optimization variables, you can give this variable bounds, like x can vary from 0 to 10, y can vary from 0 to 10. So large variable bounds will give to large search domain and difficult solutions. So you have to minimize the variable bounds to as much as possible for quick convergence of the algorithm. So now we look at graphical method. Okay, graphical method of optimization is a very basic method. In practice, nobody will use that because now so many algorithms are there. But graphical method will teach you how to visualize the feasible region and objective functions by actually plotting those values on the graph paper. The graphical method can be used in for two variables, x and y. Okay, because but if you have three variables and all, it will give a three-dimensional image, and you cannot use the graph paper. Okay, so it is useful for two variable problem, up to two variable problem. Okay, so what is the basic method of graphical method? Plot feasible region. Okay, then you have to superimpose the objective function as it passes through the feasible region, and you can find maximum or minimum values of the objective function within the feasible region. So it is just a direct method. Okay, so now we look at formulation of simple optimization problems. First, we look at single variable ones. After that, we'll plot the double variable ones. So let us look at this example. There is a simply supported beam of uniform rectangular cross section. Okay. So the variables for optimization are breadth B and depth D. So these two variables can be changed by the algorithms. So length is fixed. Okay, the value of length will be given to you. Then load P is also fixed. Okay, so then constraints are there. There is stresses. Bending stresses must be within safe limit, and deflection should be less than 1% of the span. So objective function is to minimize the weight of this P. Okay, subject to these constraints, that is safe limits, and static deflection should be less than 1% of the span. So first let us write the expression for objective function. Okay, minimize the weight W. So weight W equal to density into area into length. Okay, so only B and D are variables. Density will be given to you, length will be given to you. It will be fixed. Okay, so this way you can write expression for objective function. And two constraints are given. First constraint is that midspan deflection delta must be less than L by 100, length by 100. So equation for midspan deflection of a simply supported beam is PL cubed by 48 EI. That should be less than L by 100. So I, that is moment of inertia, can be replaced by BD cubed by 12. So you can do lot of further simplification. This L and this L cubed will cancel, you get L squared. Okay. So after lot of simplification, you will get the first constraint equation written in the standard form. Standard form is written as either less than or equal to 0 or greater than or equal to 0. So PL squared by 48 EBD cubed minus 0.01 should be less than or equal to 0. So that is the form of the first constraint. It's a inequality constraint. So suppose they said the midspan deflection should be exactly equal to L by 100. Okay, then this less than or equal to sign will go and you get equal to 10. Then the design will be more difficult because it is the range of values which will give exactly 1 mm deflection is difficult to find. So that is why we don't want to use equality constraints and we use inequality constraints. Then one more constraint is there. Maximum bending stress in the beam must not exceed yield stress. So the maximum bending moment occurs at the center of the beam. That is PL by 4 and D by 2 is the distance of the extreme fiber from the neutral axis. BD cubed by 12 is the moment of inertia. So after a lot of simplification, you get this final equation. That is 1.5 PL by BD cube minus sigma y is less than or equal to 0. So of this only B and D are variables. Okay, all others will have numerical values which we will give in the next slide. Then another thing is they are called implicit constraint. Okay, so what is implicit constraint? Implicit constraints are constraints which are not mentioned in the problem, but you have to use your intelligence. Okay, so this is actually a slender beam and it is based on Euler-Bernoulli equations because the equations for deflection, bending stress, okay, all these equations are based on slender beam equations. Okay, so for slender beam equations, the depth should be less than 1/10 of the span. So this constraint we should include. Okay, so this is the third constraint. Straight. Okay, so now let us put some numerical values. So I already told that only B and D are the variables. So all others have some fixed value. So length is 1 meter, Young's modulus of beam is given, density is given, P applied force is given, sigma y yield stress is given. So when you substitute all these values, you will get first constraint equation like this and second constraint equation like this. Okay. So this is objective function. Okay, so then we need some variable bounds. So what is the allowable range of values for B and D? So let us assume that the allowable range of breadth is up to from 0 to 0.1 meter, that is 10 centimeters. And depth is also allowed from 0 to 10 centimeters. Now let us plot this objective function versus B and D. So objective function is a function of B and D. So let us plot this objective function which will occur on the Z axis. Okay, so the surface you see is the objective function, that is W of xy. Okay, so this is the W of D and B. So this is D, this is B, and this altitude will give the W or weight. Okay, this is the plot of the two-dimensional objective function. Okay, so it will it's a function of D and B, and it will give a surface. So you can see that maximum weight is 70 kilogram. Okay, that occurs at the point here. That occurs when when D is 0.1 and B is 0.1. That is the maximum allowable values of D and B will give weight of 70 kg. Obviously, we don't want that. And you can get zero weight. Okay, all these regions will give zero weight because either B equal to 0 or D equal to 0. Okay, so one important issue here is that the constraints will not allow the beam to have zero weight. Okay, the reason is that when the B is equal to 0 or D equal to 0, then deflection will exceed more than one number, and also bending stresses will exceed more than allowable yield stress. When the B equal to 0 or B tends to 0 or D tends to 0, the cross section is so small that bending stresses will be very high. Okay, and it cannot withstand those bending stress. So constraints will not allow these low regions, and constraints also will not allow these regions. Okay, because when the in these regions the deflections will increase, so the constraint will allow us only to search some values in this middle region. So this is for the two variable optimization. So later we'll study two variable optimization problems in detail. Okay, because you have to draw contours and all that. So suffice to know that constraints will filter out absurd values like B equal to 0, D equal to 0, or B equal to 0.1 and D equal to 0.1, which will give a large deflection under no. Okay, so now this two variable graphical problem will be reduced to single variable problem by assuming a connection between B and D, assuming a relationship between B and D. Then we can start plotting the single variable problem. Okay, so let us assume that D equal to B by 2, that depth is equal to half of breadth. So we are introducing an equality constraint. So every equality constraint will cancel one variable. So if you assume D equal to B by 2, you can eliminate the variable B in this equation. Okay, so it is now reduced to one variable. Objective function is reduced to one variable. Then this first constraint, which was a function of B and D, can be converted purely to D by eliminating B. And upon further simplification, you get D should be greater than 0.033. So first constraint becomes like this. The second constraint becomes like this. That is, D should be greater than 0.0420. And third constraint is the implicit constraint. That is, D should be less than L by 10. And L is taken as 1 meter. So D should be less than or equal to 0.1 meter. And so let us plot the single variable objective function and feasible region. So let us plot feasible region. So first feasible region is that D is greater than 0.033. So this is okay, 0.033. So D is greater than 0.033 is shown here. Next is D is greater than 0.0420. So this is 0.0420. 0.0420. So D is greater than 0.0420. Then third is D is less than 0.1. So D is less than 0.1. Okay. Okay. So uh, let us look at all the intersection of this visible regions. Okay. So so D is greater than 0.0333 is this hatched region. Okay. Then D is greater than 0.0420 is this hatched region. Okay. Hatched region. Then D is less than 0.01 is this hatched region. So maybe I'll use another color. This hatched region. Okay. So you can see that this is the common area which contains the intersection of all three constraints. Okay. So this region contains the intersection of two constraints only, but this region contains the intersection of three constraints. So this is the final feasible region. Okay. So now let us plot this region and see how the objective function passes through this feasible region. Let us plot the objective function passing through the feasible region. Okay, so this is our feasible region. Okay. Okay, from here to here is our feasible region. So we are plotting our objective function, that is W equal to 14,000 D cube. So the objective function is obviously 0 when D equal to 0, and it will slowly increase with the square of D, and it will go like this. So this is our feasible region, FEAS. So the objective function is entering the feasible region at this point, and what is the value of the weight? Value of the weight is no. This is the minimum value of the weight, and here the objective function is just leaving the feasible region. So here you get maximum value of weight. Okay, max W. Okay, so minimum value of weight is obtained for D equal to 0.04, and the maximum value of weight is obtained at D equal to 0.1. Okay. Okay, so this is how you do the graphical optimization with single variable. Okay. Yeah, I think we can look at one more example and stop. So this is a equality constraint. How to solve an equality constraint optimization problem for a very simple case. So there is an open box of sides x, y, z feet. Cost of making a side panel is ₹2 per unit area. Okay, 2. So cost of making side panel is ₹2 per unit area, and the cost of making bottom panel is 3 per unit area. So what is the maximum volume which can be made exactly for ₹100? Okay. So it is a equality constraint. Okay. So the money you can spend is exactly ₹100, not more than ₹100 or less than ₹100. So X, Y, Z are allowed to vary between 0 to 6 feet. First of all, volume of the box is X, Y, Z. That is easy to know. Then cost constraint is there. Okay. Cost constraint is ₹3 into XY, that is area of the base. ₹2 into cost of the two sides, that is XZ is area of each side. Then 2 rupees into area of the other two sides. That is, area is y z. That should be exactly 100. So this is the equality constraint. So you can see that 3 variables, 1 equality constraint. Okay, so we can eliminate 1 variable based on this 1 equality constraint. So you will finally get only 2 variables for optimization. Okay, so let us eliminate 1 variable using this equality constraint. So using the equality constraint, so you can take z on the left hand side, and all the other terms can be grouped on the right hand side. Okay, so if you look here, this z is here, z is here. Okay, so z we can bring to one side. Okay, and xy terms will come on the other side. So that is what is written here. Okay, so z is written in terms of this x and y. So in the objective function, for z you replace this expression 100 minus 3xy by 4x plus 4y. So the equality constraint has been incorporated into the objective function. So there's no further need to separately consider the equality constraint. Equality constraint is already embedded in the objective function. So we only need to find maxima of this objective function with 2 variables x and y. Okay, so let us, the simplest method is to plot this surface V of xy. Okay, within the range of x and y vary from 0 to. Okay, so I plotted. Okay, so this is V of xy. Okay, V of xy occurs in the z axis. Okay, so maxima of V of xy occurs here. I have manually selected that maxima using the cursor of the MATLAB. So I draw a perpendicular down and I find the value of x and y. So x and y is, x is equal to 3.33 and y is equal to 3.33. And knowing that, I can recalculate the value of z from the equality constraint relationship. So the correct solution to this equality constraint problem is x equal to 3.33, y equal to 3.33, and z equal to 2.5. So this is equality constraint by the method of eliminating a variable. So for simple problems, you can eliminate one variable like this, but sometimes it is not easy to eliminate. So that type of examples we'll see later. So suppose you have to solve this analytically with the differential equation, with the calculus. So what you will do is that first to find the points of zero slope, you have to put del v is equal to 0, or partial v by partial x equal to 0, partial v by partial y is equal to 0. If you solve these two equations, we will get x equal to 3.33 and y is equal to also same value. Okay, then you can find z equal to 2.5. Then next is you have to check if it is maxima or minima by checking the second derivative. That is partial squared v by partial x squared, partial squared v by partial y squared. So it should be negative at x equal to 3.33 and y equal to 3.3. And if you substitute it, you will actually get some negative value. Okay, so we can stop here now. Next class we look at that that 2 variable graphical problems. So we can stop this now and then stop recording now. Okay.
Thank you so much, sir.
I'll upload the slides later. Okay, maybe tomorrow.
Okay, sir.
Okay. Okay. Thank you.
Thank you, sir.